Log on, tune in, find out. Another good idea from Cambridge.
Thank you. So thank you very much for the introduction. Before I start my talk, I would like to thank the organizers for giving me the opportunity to talk at this conference. It's a pleasure and an honor to be here. So today I would like to report on some joint work with Melissa Liu from Columbia University on the topology of moduli spaces of vector bundles on a real algebraic curve. So these moduli spaces will be described as real algebraic varieties, and we shall compute some mod 2 Poincaré series, the mod 2 Poincaré series of these real algebraic varieties. So I'll start by explaining a little bit what are exactly the moduli spaces I'm talking about, and we'll see in the process that these moduli spaces have a presentation as a quotient of some sort, a Lagrangian quotient to be precise. And so this suggests to compute the cohomology to use an equivariant approach. So I'll briefly recall in the second part of my talk the equivariant approach of a T-n bot to computing the cohomology of moduli spaces of vector bundles on curves. And then we'll see on an example how we can adapt their methods to a setting with involutions to compute the cohomology of a quotient in real algebraic geometry. Okay, so apart from the, of course, the T-n bot paper, which is absolutely central to this work, there are three references that I would like to bring to your attention. So the story of moduli spaces of vector bundles on a real algebraic curve begins with the paper by Biswas, Huysmans, and Urtubise, where they construct those moduli spaces, and then in a paper of mine I reinterpreted their construction to show that all these moduli spaces can be embedded on the set of real points of the usual moduli scheme of vector bundles on a curve. So I'll explain that in greater detail in the first part of my talk. And then what I would like to report on today is the joint work with Melissa. Okay, so just to fix my notation, so X will be a real algebraic curve, which I'll always replace by a Riemann surface, the set of complex points, endowed with the anti-holomorphic involution coming from the Galois action on the complexification of the real algebraic curve. So I shall assume that the Riemann surface thus defined is compact connected n of genus greater or equal to 2. Okay, then on such a pair, a Riemann surface and an anti-holomorphic involution, well, one can study different things. This is actually the point of view taken by Biswas, Huysmans, and Urtubise in their paper, which is to study holomorphic vector bundles over this Riemann surface, which are either real or quaternionic. So that means endowed with an automorphism tau, which is C antilinear in the fibers, and which squares to plus the identity in the real case and to minus the identity in the quaternionic case. So their paper contains, among other things, a complete analysis of the moduli problem. So that includes a topological classification for those objects, a notion of stability, and proof that there exist connected moduli spaces for stable real and quaternionic bundles of each given topological type. Yeah, maybe just to explain why there are more topological invariants than the rank and the degree on the real algebraic curve. Well, if you consider the set of real points of the real algebraic curve, it's a union of n circles, which may be 0, but which by a theorem due to Harnack cannot be greater than g plus 1. Okay? And then over each such circle, a real bundle, for instance, defines a real bundle in the usual sense, so this bundle of fixed points. And so over a circle, this has a certain topology given by the first Stiefel-Whitney class. So if you have n circles, you have n Stiefel-Whitney classes, and this was Huysmans and Urtubis show that the sum of those Whitney classes needs to be congruent to d mod 2, to the degree modulo 2. Okay, so these give some restrictions on the topology of a real holomorphic vector bundle. Okay, so as I said, I would like to introduce a slightly different, yet of course very related point of view, which is just saying that whenever the algebraic curve is defined over the reals, then so is the coarse moduli scheme parameterizing S equivalence classes of semi-stable bundles of fixed topological type. Of course, you can show that just by following the GIT constructions and checking that any Grossmanian or algebraic variety entering the construction is actually defined over the reals, or you can just look at the Galois action on the complex moduli variety, and this just induced by the functor taking a holomorphic bundle to its conjugate pullback. So because this functor preserves the rank and degree, it will induce an involution on the set of S equivalence classes. And the set of real points, of fixed points of that involution, is the object that we study. We're interested in the topology of this real algebraic variety. So as is often the case, topology for real algebraic variety will mean mod 2 cohomology with mod 2 coefficients. Okay, so a first step into the study of the topology of that algebraic variety is a sort of an interpretation of real points. So using the construction of Biswas, Huysmans, and Urtubis. And so we know now that the real points of the moduli scheme are in bijection with S equivalence classes of semi-stable real and quaternionic holomorphic vector bundles of rank R and degree D on the Riemann surface. And moreover, the connected components of the set of real points are indexed by the topological types of real and quaternionic bundles. So, so we can use the second part of the theorem to actually count the connected components. Because you see, if you want to count the topological types of real bundle over a curve which has real points, for instance, you need to consider all the solutions to this equation. And in Z mod 2Z, this has 2 to the n minus 1 solutions. So because as n is smaller than g plus 1, and there might be one connected component corresponding to quaternionic bundles, the real algebraic variety cannot have more than 2 to the g plus 1 connected components. In fact, we can count them all in all cases. Okay, so now we're interested for each of these connected components in the mod 2 cohomology. So actually, this next series of slides on the gauge theoretic approach to the problem is intended to, of course, help me reach my goal, but also to tell you a little bit about the methods involved in the proof of the previous theorem. Okay, so here I'm just recalling that whenever you fix a Hermitian, smooth Hermitian complex vector bundle of fixed topological type, rank R and D, then, and its unitary and complex gauge group, then you obtain a bijection between holomorphic structures on that Hermitian bundle and complex orbits of unitary connections. Okay? So as you are only interested in stable bundles in the moduli problem, the question is how to characterize those those orbits, that define stable holomorphic structures, right? In the slope stability sense that we all know. Okay, and this is precisely the subject of a theorem by Donaldson, where he shows that a holomorphic vector bundle is stable if and only if the corresponding complex orbit of unitary connections contains an irreducible Young-Mills connection. So irreducible means that the resulting holomorphic bundle is not a direct sum. So in terms of group action, it means that the stabilizer of the connection in the complex gauge group is as small as can be. And the Young-Mills equation for connections on bundles on a curve is just this condition on the curvature, namely that it should be constant and scalar. And Donaldson also shows that such a connection, if it exists, is unique up to the action of the unitary gauge group. Okay? And this, in fact, enables him to derive a new proof of the celebrated Narasimhan-Seshadri correspondence by showing the existence of homeomorphism between the complex moduli variety and the set of unitary orbits of polystable unitary connections. That's a direct sum of, Young-Mills connections, direct sum of irreducible unitary. Anyway, so for us, for us, the upshot of this presentation is that because of the observation by Etienne Bott that the curvature map is a momentum map for the action of the gauge group, the unitary gauge group, we obtain a presentation of the complex moduli variety as a symplectic quotient. And that was the general starting point for the study of Etienne Bott to compute the Poincaré series of the complex moduli variety by means of equivariant cohomology applied on the left-hand side, okay, since you have a quotient. Okay, so we would like to do something similar for real and quaternic bundles. So the first step is to obtain representations of those connected components of the set of real points that we know are moduli spaces for real and quaternic bundles as a quotient. So just as in the Etienne Bott picture, where a bundle of fixed topological type is chosen, here we choose a real or quaternionic Hermitian bundle of fixed topological type. So this just means fixing a smooth real or quaternic structure on the Hermitian bundle EH. Okay, so by the previous theorem, we know that this determines a connected component in the set of real points of the moduli scheme. And so it turns out that it also determines involutions of the space of all unitary connections and of the unitary gauge group, such that the moduli space defined by tau is exactly a Lagrangian quotient. So let me just tell you what the involution is. So for fixed tau, so one way of writing it is as follows. Observe, please, that I've replaced the choice of the quaternic structure tau, which is as over there, by the choice of an isomorphism phi between the conjugate pullback of E and E. And so I can define something like this, which sends a unitary connection to a unitary connection. This is very similar to the gauge action, except that phi is not an endomorphism of some bundle, but rather an isomorphism between two different bundles. So if you prefer to write it in terms of, let me call this A bar, if you prefer to write this in terms of covariant derivative, then the covariant derivative of section S with respect to A bar is this, this section of E. Okay. So the point is that this transformation is involutive, always involutive, an involution. Because if you apply it twice, then basically you get phi times conjugate pullback of phi times A, and phi conjugate pullback of phi inverse. But because of the condition on phi, this is plus or minus the identity. The other one is also plus or minus the identity, and the signs coincide, so they cancel out in the quaternion case. And in any event, you get an involution. And that involution turns out to be anti-symplectic and an isometry of the space of all connections, and compatible with the action of the gauge group and the moduli space, and the momentum map of that action. So that's why you need an involution on the group to have that compatibility condition. And then it's simple verification to show that this is a bijection. Okay, so this is where we started with Melissa, and our work basically consists in using the presentation of the moduli space of real and quaternionic bundles as a Lagrangian quotient to compute in the case, where the rank and degree are co-prime, the mod 2 cohomology of the moduli space, and in general we compute the equivalent cohomology of the fixed points in the fiber. Okay, and our method is to adapt the equivalent approach of a Tn bot to a setting with involutions. Okay, so let me just review briefly the method by a Tn bot. It consists in finding equivalently perfect stratification of the space of all holomorphic structures on the fixed Hermitian bundle E by considering the Harden-Rassmann type of the holomorphic structures. Okay, and so then this gives a description of the set C of all holomorphic structures, which is just the space of all connections, as a disjoint union indexed by the Harden-Rassmann type. And it turns out, as you know, that there is an ordering on the set of Harden-Rassmann types such that the closure of a stratum is contained in the stratum with higher index. And then for the stratification to be perfect means that the associated equivalent Gisin exact sequences break up into short exact sequences. And this readily implies that the equivalent cohomology of the whole space C is the sum of the cohomology or of the Poincare polynomials of the strata. Okay, where this exponent is the complex codimension of the stratum in the whole space. So to prove that the equivalent Gisin exact sequences break up into short exact sequences, the strategy of a Tn bot is, so here at this position I'm using the term isomorphism, in the equivariant Gisin exact sequence. This goes on. So there's one such sequence for each mu, and then this is a restriction map, and there's another restriction map to C mu, and then a Tn bot show that this composed map is the cup product with the equivariant Euler class of the normal bundle of the stratum C mu in C. And their strategy to show that this map is injective, which is enough to show that the long exact sequence breaks up into short exact sequences, is to show that this is not a zero divisor. Okay, so this this approach gives a recursive formula to compute the GC equivalent cohomology of the semi-stable stratum. Well, because here we had the contractible space, the affine space of all holomorphic structures, so its equivalent cohomology is the cohomology of the classifying space of the gauge group, and also the non-semi-stable strata have a cohomology which is just a product of semi-stable strata of lower rank. So, so you obtain this recursive formula, and to start the recursion what you need is to compute the Poincaré series of the classifying space of the gauge group. Okay, so the question is, can we do something similar in the real and quaternion cases? So we want to do that for each connected component of the set of real points of the moduli scheme, and any of these components, each of these components is so the set of S equivalence classes of real and of a real and quaternionic holomorphic structures. So it can be thought of as a GIT quotient over the field of real numbers. And then, because it is a quotient, we would like to compute the equivalent cohomology of the semi-stable strata of tau-compatible holomorphic structures. Okay. So in fact, the first observation is that the involution on the space of unitary connections or holomorphic structures preserves each of the Harden-Narasimhan strata. And the reason for that is, again, because the functor that takes a holomorphic bundle to its conjugate pullback preserves the rank and degree. So it preserves also the Harden-Narasimhan type. And then the theorem is that the Galois invariant part of the strata gives an equivalently perfect stratification of the set of tau-compatible holomorphic structures. And the stratification is perfect over the field Z mod 2Z, not over the rationals. In fact, we need to go to mod 2 coefficients because the normal bundle to the real or quaternionic strata, in general, is not orientable. So to be able to consider its Euler class, we need to speak about the mod 2 Euler class. And then our strategy is the same as the Atiyah-Bott strategy, as well, we adapt the strategy, basically putting involutions everywhere and showing that this mod 2 equivalent Euler class is not a zero divisor in the equivalent cohomology ring appearing on the screen. Okay, so as a consequence, we obtain a recursive formula very similar to the one of Atiyah and Bott. So the only difference is that, well, first the exponent, now the complex the codimension of the stratum, the real codimension is half the real codimension of the complex stratum, of course. And when considering the sum, we have to be careful of taking the sum over non-empty fixed point sets. So it may happen for some strata that there are no real or quaternionic holomorphic structures in the stratum. Okay, and then the point is that the involution we defined is again affine. So on an affine space, so its fixed point set is again an affine space. So it is contractible, and here appears the classifying space of the real or quaternionic gauge group. And again, we can express the cohomology of the non-semi-stable strata as a product of the cohomology of certain semi-stable strata of lower rank. So here Ri and Di are, of course, the integers appearing in the Harden-Narasimhan type mu. And then we get this recursive formula, which is, of course, very similar to the one of Atiyah and Bott. And so to to actually perform the computations, we need to compute the Poincare series of the classifying space of the real or quaternionic gauge group. And this is actually the main technical point of our work. First of all, everything here depends on both the type of the real or quaternionic structures and also on the topological invariance of the curve, of the real algebraic curve, so which are the genus G, the integer n, the number of circles of fixed points on the curve, and the orientation index for the quotient, either 0 or 1, this A. Okay, so as an example, here is a formula for the classifying space of the gauge group of a real bundle of rank R over a curve of type GNA, topological type GNA. So it looks much more complicated than the Atiyah-Bott formula. Perhaps a special case is when n equals 0. So this and this do not appear. And this is just the same numerator as in the Atiyah-Bott picture with 2g replaced by g plus 1. And the denominator is just the same. Okay. But in general, the formulae are all very different from the Atiyah-Bott formula. And the computation is always through the computation of a spectral sequence of one of the fibrations appearing in the original paper by Biswas, Osman, and Urtubis. Okay, so let me conclude with some examples. So in the rank 1 case, so we do not have non-semistable strata. So we just need the gauge group. And this is 1 plus t to the g over 1 minus t. So consequently, if you get rid of the part of the gauge group that acts trivially, you obtain 1 plus t to the g as a Poincare series, in fact, polynomial. And this was, of course, to be expected because in the rank 1 case, the moduli space is the Picard scheme. So the set of real points is just a g-dimensional real torus. So that is indeed the Poincare series. So now for an example in rank 2. So here I shall only consider the case where degree is odd and the structure is real. So in that case, whenever, well, actually if and only if the curve has real points, do we have a smooth connected compact real manifold of dimension 4g minus 3 as a moduli space. And then the mod 2 Poincare series of the classifying space is given by this expression. And the recursive formula is just like this. So basically, the only computation left to perform is this sum. So it's not very difficult. It's just an analysis of which strata are non-empty and then take the sum. And it gives this expression to the right. Okay, so remember that I said that this was a compact connected manifold. So it's Poincare series, which is just the result of the computation multiplied by y minus t, should be a polynomial satisfying mod 2 Poincare duality. So to check that, you just compute t to the 4g minus 3 times the polynomial in the variable 1 over t. And if this is equal to the original polynomial, series, first it forces that series to be a polynomial, and that polynomial satisfies Poincare duality. And it is indeed the Poincare polynomial of the moduli space of tau compatible, compatible holomorphic structures. In fact, with a little more computation, you can actually reach a polynomial. Okay, so this sort of computation we can do more. Of course, the difficulty is the same as in the Atiyah-Bott case, that after rank 3, the volume of computations drastically increases and it becomes difficult. But we've computed some examples up to rank 3, and just as in this case, whenever the moduli space is smooth, so far we've only found polynomials. So it should be that we're on the right track with the recursive formula. So this is where I'll stop. Thank you very much.
For your classifying spaces, do the spectral sequences all degenerate? Or?
Right. Yeah, they do for those vibrations. Yeah, mod 2, exactly, mod 2. So first, that's the first point. And then, again, so we have to look at all the cases that you've distinguished between the topological types of real and quaternionic bundles. And in each case, it's a different argument to show that the spectral sequence degenerates. So
Topology is a mess.
it is, indeed.
Yeah, did you calculate the Euler characteristic of these from these formulas?
No, not yet. So that would be the sort of, so this would be calculating more invariance is exactly where we're heading next, but we're still on that for now. Thank you.
Any other question? So if not, let's thank Florent again.